All right, and we're live. Welcome everyone to Lab 5 of the Spring 2020 semester. I'm really excited to have you all here. We're going to learn about container types, sorting algorithms, binary search, all that good stuff. And then hopefully we'll get you ready and thinking about the midterm. So let's get started. Okay, a couple of announcements. Remember that we've got Project 2 due on Tuesday. And then big note, I know that I posted about this on Piazza, but also just in general, want to make sure that you understand we've got Lab 4 and Lab 5. The quizzes are due on Wednesday at 6 o'clock p.m. No autograder portion, just a quiz. And then we've got our midterm on Thursday. Wait, these are the wrong slides. Let me grab the updated ones real quick. At least I think I have updated ones. Let me go ahead and try these ones again. So those should be at 10:20 a.m. and p.m., not 10:30 a.m. and p.m. Okay, I think we're just gonna have to roll with these slides, but they're pretty much the same. So we'll be chilling. All right. Okay, and we're back. Okay, so we'll have the midterm at 10:20 a.m. Let me correct that real quick, just for the people watching. We'll have one group in the AM, Eastern Standard Time, and then one in the PM, Eastern Standard Time. For those, you want to review all of your lecture and lab notes, understand how to do the lab coding exercises, projects, stuff like that. We won't ask you to, like, code another project on the exam. Obviously, that would be a ton. But kind of understanding the basics of what goes into those is really helpful. The exam will take place on Canvas and on Gradescope, so we'll end up having a Canvas quiz for the exam, and then you'll turn in your handwritten portion on Gradescope, where it's graded. And we'll have more details on that coming up. And then you'll have an in-class midterm review on Wednesday, which I believe will be done by the professors, so that should be really helpful too. Any questions on general announcements? Okay, cool. Looks like we're chilling. So in terms of this lab, what we're going to talk about is we'll go over a couple of the midterm topics, talk about container types, sorting algorithms, binary search, and then I'll introduce the handwritten problem. Yeah, and I think that's about it. I feel like I had something else to say here, and I forgot. So we're just going to keep going. All right, starting off, midterm. So we've got a nice little list of projects or topics to review. This is basically kind of all of the lecture material that we've had up until the midterm. We do not have string algorithms and library functions, or rather we don't have, so we have a string lecture later on in the semester. Obviously, you don't need to understand that material for the midterm because we haven't taught it yet. But the string algorithms that are related to like treating strings as containers of characters, like we had you implement in lab 3, I believe, those ones you do want to be familiar with, just because those are kind of what we expect you to be able to do. Yes. And then some of this I know you'll still be finishing up and covering in lecture, like Quicksort and merge sort. No worries, we'll give you a little intro to this to start off, and then you'll be good to go. So we had one question: what are we allowed to have with us on the exam? The exam is open book, but please don't cheat by sharing answers or anything like that. The quiz questions will all be generated from a specific test bank for each topic for an individual, so everyone will have a slightly different exam. And yeah, there are no restrictions on like a cheat sheet that's handwritten or anything like that. Good question. Okay, any other midterm questions? Also, make sure to fill out the form about whether you'll be taking it in the AM or the PM, so that we can start grouping students together for those 2 sessions. Use of IDE, is that allowed? That's a good question. I don't see why it wouldn't be allowed. I'll ask about that in the Slack and get back to you. I don't think we decided on that. I mean, I guess we can't really stop you, right? So it would make sense to allow everyone to use it. Exactly. Yeah, good point. So I'll check in with IDE usage. I feel like it should probably be fine. All right, awesome. So jumping right in with a little review of types of containers. So remember that we've got a couple of different types of containers. So we've got searchable containers, which are basically any containers that are going to support a find operation. So for example, a vector, a deck, and a list, you can find something in those, right? If I ask for, like an element 3 in this kind of container down here, I'll be able to find it. On the other hand, something like a stack or a queue isn't going to be searchable because I can't really, call .find on a stack and it'll tell me where element, 4 is or so. Or sorry, like let's say that they're integers, it won't tell me where the integer 4 is. Instead, those are kind of always going to give you elements in a specific order, but not necessarily let you search for something. Then we also have sequential containers, which are going to allow iteration over elements in some order. Sequential containers are going to be stuff like vector, deck, and list. Again, not sequential is going to be stack or queue. You can't really iterate through your elements. You can look at them one at a time, but you can't, look at all of them as they're still located in memory. Then we also have the difference between sorted and ordered containers. So if we think back to lecture, we want to remember that sorted containers, the elements are going to be stored in some predefined order based on a sorting criteria. And that sorting criteria is going to be maintained by the container itself, which is why a sorted container doesn't support insert into any location. When you call insert on a sorted container, that container is going to take the object that you'd like to insert. It's going to, based on that predefined order, kind of take a look at where it should belong, and then it will insert that location or insert that element into that location. But you yourself can't just insert an element into any location in a sorted container. Sorted containers are going to be really convenient if we want to search the container because they give us faster time complexities, right? We can use binary search to find elements, so that's going to be O of log n in certain conditions, and in general, there are a lot of operations that can just be sped up by having sorted elements. So an example of a sorted container would be something like a map or a set. On the other hand, we also have ordered containers, which are not necessarily different from sorted, right? You can have an element or a container that is sorted and ordered. An ordered container is going to just maintain a current order, which means that the relative ordering between elements will remain the same as long as you use valid operations on that container. An ordered container is going to support insert at any location because you yourself are kind of maintaining the order of the container. Wherever you insert something, the container will guarantee that the relative ordering between that element and all the other elements will remain the same. So insertion and deletion will maintain that, but it doesn't have a predefined order based on its sorting criteria because it's not sorted. So examples of this would be a vector or a deck or a list. And so an ordered container and a sorted container don't necessarily need to be implemented as just an array or just a linked list, but those are typically what we kind of think of. And we have different time complexities for these operations on arrays or linked lists based on ordered and sorted containers because the way that operations are done kind of differs between them. So if we take a look at, for example, insert after on an array and a linked list. If we want to think about, one of the things that we want you to become comfortable with in this class is understanding where the time complexity of a specific function comes from. So for example, if we're calling insert after in an array, finding, the place to insert after, let's say that we have all of these, and let's say that we have some integers in there. And let's say that I want to insert after this element. Let's say that I want to insert an 8. If I, call insert after and I specify exactly where I want to insert with, my time complexity of O of n isn't going to come from actually needing to insert that item. It's going to come from the fact that in order to make space for that item, I need to shuffle all of my elements over one and copy those in memory before I can insert my new item. Does that make sense? Okay, makes sense. Awesome. And so when we're thinking about, the complexity, the time complexity of an array, oftentimes that time complexity has to do with the fact that it's contiguous in memory, right? So if it's contiguous in memory, when we insert something, we need to maintain that, which is why we need to copy everything over. That's where that time complexity comes from. Same thing with delete, right? If we call delete on an array and I want to get rid of an element, again, I need to copy everything over, except I have to shift it over in the opposite direction. And so that's, again, where my O of n operation is coming from. On the other hand, when I have operator bracket on an array, because we're going to use index arithmetic, pointer arithmetic, there we go, we'll be able to just do all of the math of, okay, which memory location is this element at? And then I can just go look at that memory location and grab it. So that's why it's O of 1. A linked list, on the other hand, if we think about a linked list, right, we have all of our elements like this. And then I have my head pointer pointing to the front. If I want to insert after a specific element here, and I already know where that element is located, I'm only going to do a constant amount of operations in order to insert something after that, right? So I can go ahead and here's my new element I want to insert. I can just repoint the next pointer of where I'm inserting after to my new element, and I can use that next pointer that it was the element that the next pointer was previously pointing to kind of point my new element's next pointer into the rest of the list. So I'm always just going to have to move around the same number of pointers. That's always going to be a constant operation. On the other hand, when I have something like a bracket operator where I want to index into a certain location in the list, because this is a singly linked list, I'm going to have to start at the head pointer, and I'm going to have to travel, the exact number of steps that I need to in order to get to the bracket index location where I want to look. For a delete, because we're able to kind of move around the pointers, again, we can just get rid of that in O of 1. Of course, the complexity of that might also depend on if you have previous and next pointers, so whether it's a doubly or a singly linked list. Good on ordered containers? Okay, awesome. Thank you, Evan. All right, so then in terms of sorted containers, the big benefit that we're going to get from sorted containers is that we can use binary search, right? But the problem with binary search is that the benefit that binary search gives us is only really a big benefit if we can use operator bracket, right? Because binary search is basically saying, okay, I'm going to take this entire array and I'm going to cut it in half. And then depending on which side I need to go to, I'm going to cut that side in half and that side in half and so on and so forth. But in order to, cut that array in half in a short amount of time, I need to have my bracket index operator be really fast. And so on an array, we're able to do that, right? We're able to do find in O of log n because we can do binary search via the square bracket operator. And it's the same square bracket operator, which is why we're good to go here. On the other hand, with the linked list, when we call find, we can't really do binary search on a linked list, right? Because even if I have, let's say that I have 5 elements, in order to cut this list in half, right, the first step / stage of binary search, I'm going to need to start at the head pointer and actually go through half of the list in order to get to the middle element. So at that point, I've already looked at half of the elements, and it's not really going to help me to backtrack to get to half of that. And so when I'm looking through a linked list for a specific element, when I'm calling find on a linked list, I'm just going to end up traveling through the entire list like this. And so that's where my O of n complexity comes from, because we're not able, because our bracket operator takes O of n here, we can't really use binary search like we could in an array, so we're just going to have to iterate through all of the elements. Okay, awesome. So in terms of practicing this, let's go ahead and go through an example problem. So thinking about the concepts of ordered and sorted. So our question was from fall 2018. And the question is, which one of the following statements is true about the contents of the underlying data vector used to implement a binary heap? Quick question, have you all covered binary heaps in lecture yet? Yeah? Okay, great. That was yesterday. Okay, awesome. I knew it was coming up soon. I wasn't sure if it was if it had already happened, but it has. So that's great. This is good practice then. Okay, so we're basically trying to decide whether a binary heap's underlying data vector is ordered, sorted, one of those, neither of those, both of those. And so um, real quick, so in a normal lecture or a normal lab, I would typically give students some time to try out this problem, and then we'd reconvene and kind of go through the answer. In a recorded format like this, I'm still totally down to give you guys some time to try out this problem, and then we'll reconvene and go through it together. Can you real quick, just in the chat, tell me if you prefer some time to try it out on your own, or if you prefer just going through it as a group? Okay, awesome. So it seems like a lot of people like having a chance to try out the problem on their own first. So why don't you take, let's do 3 minutes or so to try out this problem, see what answer you get, and then at 3:24 p.m. we will reconvene and go through the solution together. All right, so let's go ahead and go through it together. So to start off, we're going to reveal the answer, and then we'll kind of go through how we got there. So the correct answer for this question is D. The binaries heap's underlying data vector is neither an ordered nor a sorted container. And now let's go through why. So to start off, we want to kind of remember how the underlying data vector looks, right? So we have the relationship between the nodes is only that no parent is lower in priority than any of its descendants. And so there are multiple array representations of the exact same binary heap. So for this binary heap, right, we have 6 unique elements, and you can see that we can have a valid min heap and an identical min heap, both of which are valid min heaps with these elements. And because we have variations, when we have unique elements, this will show us that the binary heap is not sorted. So if all of these elements were unique and there was only one specific way to write this heap, then we would see that it's sorted, but because that's not the case, it's not sorted. The data in the vector does not have to be in a specific order in order for the binary heap to be valid. Now, in order to show that it's not ordered, we want to determine a situation where adding an element changes the relative ordering of elements already in the heap, right? So remember that ordering has to do all with that kind of relative ordering between elements. So we're going to try to come up with a scenario where we end up reordering elements. And so we came up with this example. So let's say that we have a binary heap that looks like this. Quick question, is this going to be a max or a min heap? It's going to be a max heap, right? Because we've got our top element here is 8, which is kind of like the maximum of these elements. And then remember that there's no relationship between its children, right? Both of those just have to have a lower priority than their parent. And so let's say that we want to add the element 9 to this binary heap. So remember that we're going to go ahead, insert it at the bottom location, and then call fix up on it. So we're going to go ahead and swap with 2. We're going to call fix up again. We're going to swap with 8. And we're going to end up with this kind of final heap. So our new array representation is going to be 9, 8, 4, and 2. And so if we take a look at the relative ordering between these elements, we see that 8 is still before 2 and 4, but we see that 4 is in front of 2, and it's no longer 2 in front of 4. And so we can see that the relative ordering between elements changed. So in this case, our binary heap, or kind of vector representation, is not ordered. Any questions on that? Okay, great. I know that we had one question earlier which asked if it was better to do the extra handwritten problems for each lab or if it's better to drill LeetCode. This student felt like LeetCode kind of messes them up if a random problem isn't particularly geared towards something we've covered. Well, one day I'll be able to speak without typos. I would recommend, I think that either of those approaches is really helpful. I do know that the extra handwritten problems for each lab are a little bit more tailored to the course content. So that can be helpful just if you're trying to get used to the material itself. I found that LeetCode is really helpful for going through the process of approaching a new problem. So I feel like, going through multiple problems on LeetCode can be really helpful in just, getting a problem statement, needing to break it down into its components, thinking of a potential solution, implementing it, and then seeing if there's a better way to do it. I think that both of them are really helpful for the exam. I know that in the past when we had in-person exams, I used to also recommend to students that they practice writing those by hand, just because that was what they would be doing in the exam. And so the more practice you have handwriting code, the easier it is to do that during the exam. But because you're able to type out your handwritten portions, I think you are. I wouldn't worry about that too much. Okay, cool. Then if there are no other questions, let's go ahead and move on to, yes, so we do have another question. It says, I'm kind of confused how the data doesn't have to be in a certain order. I know there are multiple orders, but the heap still has to maintain an order. Right, so when we're thinking about order and sortedness, we're thinking about all of the elements in relationship to one another. So in this case, the heap still has to maintain an invariant, but that invariant itself doesn't necessarily imply one specific order. So the heap says that every parent has to have a higher priority than its child for a max heap in this case. And so no matter what we insert, our heap will always fix itself so that that itself is maintained. But the relative ordering between elements will change, which is why the heap itself isn't by definition ordered. I think if you look online, you'll see that heaps are actually, they're called semi-ordered because they have that invariant that means that, there's some relationship between elements, but because that relationship isn't fixed between like children itself, right? Like if we have 8 and 4 here, it doesn't matter that we have the 8 on the left and the 4 on the right. We can swap those and it'll still be the same. But that's why it isn't ordered. For sorted, if we think about the ordering for sorted, so the reason that it's not sorted is because a sorted invariant will tell us that, okay, if we have a unique set of elements, right? So let's say that we have 1, 2, 3, 4, 5, 6, then there's going to be only one valid way for us to have those because our sorted the sorted invariant will by necessity tell us exactly which element needs to come before which. And so in this case, so the two heaps on this slide are identical because they're both valid min heaps. So the one on the top is going to look like this. So we'll have 1, 2, 3, then 4, then 5, and then 6. And over here we will have 1, then 3, then 2, then 6, then 5, then 4. And so they're not necessarily identical in how they're drawn or how they look, but the relationships that they represent, they all have the same number and type of element. So they all have 1 through 6, and they're all a valid min heap. So this is a valid min heap, and this is also a valid min heap. And so they contain the same elements, and they're both valid min heaps, so that's why they would be considered identical. And so the ordering that they maintain is between levels, but there's no rule about anything beyond that. And so not all of the elements in a relationship to one another have one rule for how they need to be maintained. Does that make sense? Okay, awesome. All right. So then let's go ahead and move on to sorting algorithms. So for sorting algorithms, we want you to consider a couple of things for all of them and be able to compare them based on these. So we want to think about time complexity. For me, it usually helps to also consider edge cases. So for example, if my input to this sorting algorithm is already sorted, what will my time complexity be? What about if it's in reverse sorted order? And then what about if it's like a scattering of sorted? Some of the elements are sorted, some of them aren't. Our time complexity will kind of have our best case, worst case, and average case scenarios, and those might change based on this type of input for different algorithms. Then we also want to think about the space complexity. Is this a sort that is done in place, or does it require an entirely new, O of n vector allocation? We also want to think about recursion. Is it tail recursive? If not, what is the stack depth? That's going to relate to our space complexity, right? And then stability. Does it preserve the original ordering of the elements that are equal? Or does it, swap them potentially? And then adaptability. Does it perform optimizations based on the order that the elements are already in? And so the sorts that we're going to be talking about today in lab as a review are going to be our 3 elementary sorts. So we've got bubble sort, selection sort, insertion sort, and then we have our more advanced sorts, merge sort, quicksort, heap sort, and counting sort. I believe we took counting sort out of these slides, so we don't have to worry about that as much. And then this is a really helpful site for kind of visualizing these sorts. It'll give you an example input, and you can step through all of the individual operations to see kind of like what the algorithm is doing and kind of take it step by step. I know that some of these more advanced sorts you haven't necessarily covered yet in lecture. And so this will be a review of what you've already covered and an introduction for the stuff that you haven't yet. So it might be helpful after you've covered the material in lecture to come back to these slides and step through them again on your own, or to kind of use this time as an early introduction to those concepts so that when you're in lecture, it's a little bit easier to follow along. All right, so to start off, we're going to take a look at bubble sort. So for bubble sort, we're going to have these kind of characteristics. In the best case, we're going to be able to stop bubble sort in big omega of n, so in one pass through the entire vector. And that's going to be possible if we keep a Boolean swap flag to indicate if any swaps were made during each pass of the array. And if we get all the way through on the first pass and we see that no swaps were made, then we know that the array is already sorted and we can end then. So that's kind of where that best case runtime comes from. In general, though, we're going to end up with average case and worst case O of n squared, because we're basically going to have to compare each element to all of the other elements, and we're going to have to do that for each element. So it's going to be kind of n times n, giving us O of n squared. The algorithm, we're going to just repeatedly step through the list to be sorted, comparing each pair of adjacent items and swapping if they're in the wrong order. Each time we're going to pass through a smaller section of the list until no more swaps are needed. This is going to be stable because swaps only happen for elements with different values. And so this is kind of our high level outline to keep in mind. And now we're going to step through an example of bubble sort. So it's very nice. We have a ton of bubbles here. And now we're going to sort the bubbles. So to start off, we're going to start with our first two elements. And we're going to compare them to see if they're in the correct order or not. In this case, they're not in the correct order, right? 38 is less than 53. So we're going to go ahead and swap those elements. Then we're going to increase our pointer, and we're going to look at the next set of two elements, again, checking if we need to swap them. In this case, 53 is less than 76. So these two are already in the correct location. We don't need to swap. Next, we'll compare the next two, 76 and 29. 29 is less than 76. So we're going to go ahead and swap these two elements. Next up, we're going to compare 76 and 61. 76 is greater than 61. So again, we're going to swap these two elements. Same thing goes for 76 and 53. Same thing also goes for 76 and 14. And same thing goes for 76 and 42. So in this version of bubble sort, our larger elements bubble to the top. So after one pass through of bubble sort, you'll see that our maximum element is located at the very end of the array. And that's kind of the case. That's also why this is called bubble sort, because the largest values will always bubble to the top. So after the first pass of bubble sort, the last element is going to be in its correct location, and it's going to be the largest element. In the second pass through, we'll end up with our second largest element in the second to last position, and that will also be its final position. Make sense? I'm going to, indeed, okay, wonderful. So let's go ahead and let's do a second pass through. So again, we're going to look at these pairs of elements, pairs of adjacent elements, and we're going to swap them if they need to be swapped. So 38, 53, good to go. 53 and 29, on the other hand, need to be swapped. So we're going to go ahead and do that. We're going to swap 53. We're not going to swap 53 and 61. Those are in the correct order, but we will swap 53 and 61 here. 61 and 14, we're going to need to swap. And 61 and 42, we're going to need to swap. And again, at this point on the second pass through, we can stop early because we already know that this was our max element. So that one had already been handled in the last pass. Now, after the second round is done, we can consider this entire set of two elements to be already sorted. And so we can stop when we've compared to 42 on the next pass through. So we're going to go ahead and do that again. We're going to swap here. Note here that this was our original first 53, and this was our original second 53. And because this is a stable sort, we're only going to swap elements if they are strictly greater or strictly less than one another. In this case, if they're equal, we'll just leave them. And that's how we're going to be able to maintain stability. So we'll end up with the first and the second 53s both remaining in the same relative ordering to one another. On the other hand, we're still going to need to swap 14 over here and 42. All right, we're going to do another pass through. You'll see that each time we're ending a little earlier because we're considering all of the elements at the end to be sorted. So the amount of space that we're working through is always a little bit less, but still, you know, n-1. And here we go. So on this last pass through, we're basically going to check our two elements, see if they need to be swapped. Nope, and we're all done. If, let's say that we had ended up with, you know, these all in sorted order, and we were on our fifth pass through, so we were just iterating through those elements, and we got all the way through without making any swaps, then we could also stop early at that point because we would know that that entire section was also already sorted. All right. Any questions on bubble sort? Okay. Looks like we're feeling good about bubble sort. Awesome. So our next elementary sort that we're going to recap is going to be selection sort. So remember that selection sort, our algorithm is going to be, we're basically going to divide our input list into a sublist of, oops, let me make sure you can still read this. Sublist of sorted items and a sublist of unsorted items. Then we're going to go through and we're going to select the smallest item of the unsorted portion, and we're going to swap it into the sorted portion. This is always going to increase the sorted portion size, and we're going to repeat this until the whole array is sorted. Because we're only ever swapping elements within their own array, we don't need any auxiliary memory. So our extra memory is going to be O of 1. So this is a good sort when auxiliary memory is limited. And though this sort itself isn't stable in the O of 1 memory implementation, we can use additional memory to make the sort stable by breaking ties using the original index. So in order to keep track of the original index of elements, we'll need to have another array that kind of stores that information. And so if we have an extra O of n array, then we can make the sort stable, breaking ties in this way. But in general, we're going to find that any way we write it, we're going to end up with O of n squared time complexity. I believe this is a really good sort for lists that are already mostly sorted. And so there are still times when these different sorts can be a better choice than one of the other sorts. But in general, like if you were just going to use selection sort to do all of your sorting, it's not going to be the best idea. All right, so this time we're going to be looking at sacks of potatoes. And so each time, remember, we're going to be looking for the smallest element of the unsorted array, and then we're going to swap it to the end of our sorted array. And so in this case, everything is unsorted. So we're going to go ahead and look for our minimum value seen so far at each traversal. So we're going to go through 38 is less than our minimum value so far, which is 53. So in this case, we're going to update our minimum value so far to be 38. Then we're going to keep checking through the rest. When we find an element that is less than our minimum so far, we're going to go ahead and update our minimum so far. Going all the way through the unsorted portion. And once we've made it to the end, we're going to take that smallest element and send it to the first index. So we're basically going to swap it with the end of the sorted array. So now we can consider 14 to be in our sorted array, and the rest of this array is considered unsorted. And then we're going to go ahead and do the same thing. So looping through the sorted portion, or sorry, the unsorted portion, we're going to find our minimum element, updating that minimum element as we go. Once we found the minimum element, we're going to go ahead and swap it into the correct position at the end of the sorted position, or the sorted portion of the array. So now our sorted portion would be considered 14 and 29. Going to go ahead and do that again. Swap, and again. Swap, and one more time. So we want to note here that selection sort is not stable. This current 53 was actually after the other 53 prior to sorting, but after this sort, it will come before the other 53. And we did that swap a couple slides back when we did our first swap here, I believe. Almost there. So you'll see that our initial 53 was this first element. And when we swapped it with the 14 here, it ended up being swapped after the second 53. And so that's why selection sort isn't going to be stable unless we have a way to break ties in this way, because when we're doing these swaps, we might end up swapping the same element, kind of like numerical value wise, to the end of the array. All right, moving back. Okay, so then we're going to go ahead, finish this up. Again, looking for the minimum element, swapping it back, and we're done. Any questions on selection sort? Okay, looks like we're good to go on selection sort. Let's go ahead and take a look at the next of our elementary sorts, which is going to be insertion sort. So for insertion sort, we're basically going to take each item and insert it into the correct location when only considering all of the elements before it. So we're basically going to just swap left until it's in the correct position where it belongs. This one is very efficient on almost sorted lists, and it's one of the fastest sorting algorithms on small input sizes. So this might be a sort where you start with one of the more complex sorts to begin with, and then when your input size ends up getting to a small enough size, you switch over to insertion sort because this sort is really fast for those specific cases. In our best case, we're going to be O of n, and then average case and worst case, still O of n squared. We don't need any additional memory, and it is stable. So this time, let's take a look with some ice cream. So we're going to go through, we're going to take an element, and again, we're going to sort it into the correct position in the sorted vector, or the sorted portion of this array. So in this case, our sorted portion is empty, so we're just going to go ahead and insert 53 there. Next, we're going to take the next element, and we're going to insert it into its correct position in the sorted array. So our sorted array right now only contains 53. We're going to go ahead and swap it with elements in that sorted array until it's in the correct position. We're going to swap it with 53, and then it's in the correct position. 76, we're going to go ahead. We don't need to swap it with 53, so we can just go ahead and insert it. Our sorted array is now these three elements. We're going to go ahead and do the same thing with 29, swapping until it's in the correct position. Same thing with 61. Same thing with 53. And you'll see here again that because we're only ever doing swaps with elements up to the point where they're less than or equal to, we never swap two items that are equivalent. So in this case, we wouldn't swap 53 with 53, which means this is going to be a stable sort. Same thing with 14. Swap everything over, and 42. And there we've got insertion sort. For me, it helps to remember the difference between selection sort and insertion sort, because I would sometimes get those two confused. I would think of selection sort, I need to go select the smallest item. For insertion sort, I'm just taking a random item, or not a random item, just the next item, and then the work is done in trying to figure out where to insert it. So that's kind of how I keep those two distinct in my head. Any questions on insertion sort or any of the elementary sorts in general? All right, looks like we're feeling good. So now let's move on to some of the more complex sorts, and we're going to start off with merge sort. So merge sort, we're going to take a list, split it in half. We're going to keep recursively splitting both halves. We're going to combine our halves with the merge function, and then basically recurse up from there, and we'll end up with an entirely sorted list. Our base case is going to occur when the halves have length 1, so when we're basically taking one individual element, which is necessarily sorted, and combining it with one individual element, which is also necessarily sorted, and combine those two, merge those two together into one array. And so the main idea here is that we're only ever merging sorted arrays. And so when we have two sorted arrays and we want to merge them, remember that we can use that really helpful kind of iterative method that we talked about in lecture. So let's see an example of this, and we'll walk through what that merge step looks like. So to start off, we can either do this top-down or bottom-up. Essentially, if we're doing a top-down approach, we're going to first go ahead and recursively break up our array into smaller parts. So we're going to go ahead and split them in half, split them in half, split them in half, until we end up with a base case of 1. And then as we recurse back up from these, or kind of like as we return back from these recursive steps, we're going to end up returning sorted arrays of a larger size. But you can also do it bottom up by just starting with elements of size 1 and combining them that way, and then taking larger element sizes and combining them that way. But to begin, we're going to go ahead and just look at the first two items. So remember, we want to think of these as two sorted arrays. So we've got our first sorted array over here on the left, and we've got our second sorted array over here on the right. And we're basically going to iterate through those sorted arrays and merge them together. So I'm going to go ahead and think of this additional array that I'm going to copy elements into. I'm going to compare the two values. 38 is less than 53, so I'm going to go ahead and insert 38 first. I'm going to increment this pointer. It's at the end of the array, so I'm going to go ahead and copy in 53. And we'll end up with this sorted array. We're going to do the same thing for the next two individual elements. Combining them, 29 is less than 76. In this fashion, same thing with these two, 53 is less than 61. So they're going to be combined like this. And then 14 is less than 42. So we're going to go ahead and combine them like this. Then we're going to go ahead and we want to note that all of these individual arrays are also sorted. And so we'll be able to merge them together to make another sorted array again. So we'll take a look at these first two, and we're going to go ahead and merge these two sorted arrays together into one larger sorted array. So same as in lecture, we're going to go ahead and we're going to basically do this starting with two pointers to the beginnings of the two arrays. We're going to go ahead and compare their values. So 29 is less than 38. So 29 will come first. Then we increment our pointer. We compare again. 38 is less than 76. So we'll have 38 next. Increment the pointer of 38. Now we're comparing 53 and 76. 53 is less than 76. Increment that pointer. We're at the end of this array, so we're going to go ahead and copy everything from this pointer pointing to 76 until the end of that array. So we'll end up with 76 here. And with the puzzle pieces themselves, that'll look a little bit like this. And then we're going to do that exact same thing over here on the right-hand side. Again, we'll start with our two pointers, one to the beginning of each sorted array, and we'll compare the values. So 14 is less than 53, increment that pointer. 42 is less than 53, increment that pointer. Nothing left in this array, so we'll just copy the rest of the contents of the other array. And we'll end up doing the same thing with puzzle pieces. And then last but not least, we're going to go ahead and do that at one more level. So again, we'll start off here with our two pointers. 14 less than 29, increment. 29 is less than 42, increment. 38 is less than 42, so we're going to increment again. 42 is now less than 53, so we're going to increment here. 53 and 53. It doesn't really matter which one we choose. In this case, we might always choose to go with the one from the left-hand side to keep this stable. So we'll go ahead and keep that. Increment here. We'll end up with another 53 from over here. And now we've got 61 from here and 76 from over here. And back to the puzzle pieces. We'll just do that same thing like that. And at the end, we've got our completely sorted array. And so merge sort is a really, really helpful algorithm. It's also really great when it comes to complexity analysis, because this is like the example that you can use for Master's theorem, right? So if we think about this, we can break down our function, our recursive function, into its components. So we're going to recurse on half of our input, the left-hand side. We're going to recurse on half of our input, the right-hand side. And then we're going to merge those two halves together. So we've got the time to sort the left half, plus the time to sort the right half, plus the time to merge the two halves. That's going to give us 2t of n over 2 plus n, with our base case t of 1 equals 1. And if we use Master's theorem, we end up with theta of n log n. And so in general, there's nothing that we can really do. There's no extra check that we can do to check if our input is already sorted. And so in this case, best case, average case, worst case, we're always going to end up with n log n. We're going to need that extra memory. That extra memory is going to come from either merging into different arrays when we're actually sorting them, or merging the sorted arrays together, or that memory will come from needing to build up our stack frames in order to actually, run this algorithm recursively. It is going to be stable, however, which is nice. Real quick note, or just question to you all. Why is stability helpful? In what scenario would I want a stable sort? If we have many keys, yep, it might be helpful if we've already pre-sorted a list, or if we've already run one specific sort on it, and then we want our results to sort again. So if we think about, let's think about a file system, for example. Let's say that we have all of our files, and we have, a name. Oh wow, and then maybe a date. And let's say that I sort them all by name first, and then I want to sort my results by date, but I still want to maintain my names in order. For file systems or for sorts that kind of require this, I'm going to sort it by one thing first, and then I'll sort it by the other. Stable sorts can be really helpful because they'll keep your results in order from the previous sort, and you won't need to go hunting for them again. So that's why we care about stability. It's for those specific applications. Okay, back to merge sort. So in general, right, this is going to be our comparison-based divide and conquer algorithm. We have the bottom-up and top-down versions available. We already went through the algorithm, but as a recap, we're basically going to divide our unsorted list into n sublists, each containing one element, and we're going to repeatedly merge those sublists to produce new sublists until there's only one sublist, the final sorted list, left. Stable as long as the merge is stable, not adaptive. Memory is going to be O of n worst case because most implementations merge into a separate container and then copy over to the original container. So we have a question, isn't using a functor with tiebreakers easier than doing two sorts with the second one having to be stable? So this kind of depends on your application. In most scenarios, or in most kind of like small scale scenarios like this, where we're sorting individual elements that are, maybe like an integer or so, then having a functor with tiebreakers would be much easier, right? We don't need to sort this O of n log n and then do another O of n log n. We can just go ahead and use that specific functor. But if we're thinking about something like, let's consider a file system or so. Right, with this example of name and date, and maybe, date created, date modified, maybe the file size, stuff like that too. The more information an individual element has, the more kind of space it takes up, right? The less we want to move it around. And the less work we also want to have our functor do. So in the case of something like that, I could basically do a sort. Remember that we want our functors to be really fast, right? We want them to compare as few elements of a custom class as necessary. And so it's going to be much faster for me to first take a look at, all of the date components and sort them by that, and then use another functor to look at only all of the name components and then sort those results with that, than to have one specific functor that is constantly checking multiple different variables, because in general, it'll just take longer to run even just one individual sort on that. And so in this way, if we break it up into these different sorts, we can basically optimize each sort individually and then just run them one after the other. And it might be possible that, just sorting by date is enough for one user, and so we don't need to do that additional sort every time. And we can choose to only do that additional sort if the user specifically requests it. Yeah. So it kind of depends on your use case. Yeah. All right. Awesome. So now let's talk about Quicksort. So let me check the schedule of contents real quick. I'm not sure if you've covered Quicksort yet. Okay, yeah, Quicksort you will be covering tomorrow. So we're going to basically go ahead and treat this like an introduction to Quicksort. And then hopefully tomorrow you'll be able to just really focus on the details, and you won't have to worry about that being the first introduction to Quicksort ever. All right, so we'll start off the big picture. Quicksort is also going to be a comparison-based sorting algorithm. Most implementations are going to be unstable, except for a really complex in-place partitioning. So for our intents and purposes, it's basically not stable. And this one is often faster in practice than other n-log-n sorting algorithms. I believe this is actually the version of sorting that the STL uses. And then at a certain point, it switches over to a different sort for really small kind of n components of this sort. But basically, our algorithm is going to go like this. We're going to pick a pivot from the list, and then we're going to reorder the list so that elements with values less than the pivot come before the pivot, while elements with values greater than or equal to the pivot come after it. After partitioning, the pivot is in the final position. This is going to be key. And then we're going to recursively sort the sublist of elements with smaller values and the sublist of elements with greater values. All right, so let's go ahead and take a look at this together with an example. So for Quicksort, we need to first pick a pivot. So for this example, and I think in lecture you also use this methodology, we're basically just always going to pick the last element as the pivot. So we're going to go ahead, we're going to choose 42 as our pivot. Then we're going to take 2 pointers. We're going to have a left pointer and a right pointer. The left pointer, we're going to increment until we find a value that is greater than or equal to the pivot. The right pointer, we're going to decrement until we find a value that is less than the pivot. So let's go ahead and increment our left pointer. 53 is already greater than 42, so we're good. We can just hang out here. Now we're going to go ahead and decrement the right pointer until we find an element that is less than the pivot. In this case, 14 is already in the correct location, or 14 is already less than the pivot. Once we have the left pointer pointing to something that's greater than the pivot, the right pointer pointing to something that's less than the pivot, we're going to go ahead and swap those 2 values. Then we're going to go ahead and do the same thing. So we're going to increment our left pivot until we find a value that is greater than 42. So 38 is less than 42. We're going to skip over that. 76 is greater than 42, so we're going to stop there with our left pivot. Or sorry, left pointer, not left pivot. The right pointer, we're going to decrement until we find something that is less than our pivot. So 53 is greater than 42, 53 is greater than 42, 61 is also greater than 42, but 29 is not. Once we have these 2 pointers pointing to these elements, again, we're going to go ahead and swap these elements. Then we're going to go ahead and do the same thing. So we're going to increment our left pointer. And then, oops, when our left and our right pointer are equal, we basically know that everything to the left of that left pointer is less than our pivot. Everything to the right of that pointer, of the right pointer, is greater than or equal to the pivot. So we can go ahead and swap the pivot with these pointers. And so now you'll see that everything to the left of 42 is less than 42, and everything to the right of 42 is greater than or equal to 42. And this is a really interesting point of Quicksort, 42 is in the correct position. We're never going to have to move the pivot after we've swapped it into its correct location. That will always be where that element ends up in the end. So there's actually a, what is it called? There's another algorithm that makes use of this. Shoot, I can't remember its name. I have to find it. But basically, it makes use of this, and it basically calls, it's called Quickselect. That's the one, I think. Let me look it up real quick. Yes, the Quickselect algorithm you can use to find the kth smallest element in an unordered list by basically making use of this. And as soon as something lands in the kth smallest position in your list using this partitioning system, then you know that it's in the correct location and you can stop and just take that element. So you don't need to actually go through and sort the entire list, which is pretty cool. But for Quicksort, we still have some work left to do. We're going to basically go ahead and run Quicksort on the elements in the left partition, and then again on the elements in the right partition. So again, we'll grab the last element as our pivot, and then we're going to have our left pointers and our right pointers. In this case, we're going to increment our left pointer, and our right pointer will end up pointing to the same thing. We'll swap 29 and 38. That side will be sorted, and then we'll do a similar thing on the right-hand side here. And so when we think about this behavior, right? So we have a couple of questions when it comes to Quicksort. So if we look back at our summary slide, we see that even though in the best case and in the average case, Quicksort runs in O of n log n time, in our worst case, it runs of O of n squared time. And so if we think about where that comes from, we want to take a look at this slide. Oh, this slide. There we go. So if we want to think about where our worst case comes from, let's actually start with a better question. In what scenario, what size are my two subhalves in an ideal partition? N over 2. Exactly. In an ideal partition, we're going to end up with half of our elements on the left and half of our elements on the right. And we'll basically end up with a similar time complexity as merge sort, right? We'll always be doing work on half, be doing work on half. If we want to think about the worst case time complexity, we basically want to try to imagine, like, what's the furthest possible we could get from n over 2? And that would basically be if our partition was always located exactly at the end. So let's say that we had an already sorted array, right? 1, 2, 3, 4, 5, 6. If I always chose the last element as my pivot, and I started with my left and my right pointers, right? I would basically increment my left pointer all the way through all of these elements. And then I would basically go ahead and end up swapping 6 with 5 in this case. Or no, 6 would just swap with itself because we'd end up getting left all the way over here up to 6. So 6 would swap with itself, but we'd still have to travel through all of those n-1 elements, right? Now we can split our partition, but there's nothing on the right-hand partition, and our left-hand partition has n-1 elements in it. And let's say that we choose 5 over here, then again, we're going to run through these n-1 elements for this, this subarray, right? And again, we're going to run through n-1 elements. So what we'll end up doing is for n elements, we're always going to run through n-1 other elements. And so we'll end up with our n squared complexity. So our worst case is going to be if our pivot choice is basically always our max or always our min. Right? So when the smallest or largest element is chosen as the pivot every time, then we're going to have a really uneven partition and we're going to have the worst case performance. Because we're not really benefiting from any of the, we're not really like splitting our work in half as much as we're just always taking one away. And then we still have the rest of the work left to do. So we're decreasing it by a constant amount rather than cutting it in half. Our ideal pivot choice, right, as Eleanor found, was that we basically want to find our median element. We want to most evenly partition the array so that it's roughly, we have roughly equal numbers of elements both to the left and the right of the pivot. But in order to find the median, right, if we wanted to find the true median, what would we have to do? Sort it. Exactly. And what are we trying to do? We're trying to sort it. So rather than finding the exact median, what we can do instead is take the median of a sample. So we might look at 3 elements in the list or in the array and take the median of those. Or we might look at 4 or 5, you know, some amount. I think typically 3 is good, but we'll always look at a constant amount of elements and take the median of that. That way we don't need to sort the whole list, but we still will have a better chance at getting a better pivot choice. So we hopefully won't, we at least won't end up with the max and the min each time. Okay, any questions on Quicksort? So the question is, what about just randomly selecting an element? So even though it seems like if I randomly select an element, um, we're going to be able to, like in general, we'll end up with something that's better than the worst case scenario. It doesn't guarantee that. So we could choose a random element and chances are it'll run fine, but it doesn't guarantee that. If we take the median of a sample, it guarantees that we at least won't always have the max or the min element. So if we're thinking about, so for example, sometimes we'll think about time complexities, right? So one question that we might ask when it comes to Quicksort or so is thinking about these time complexities, where this time complexity comes from. Let's say that, you know, in a breakthrough in computer science, all of a sudden you're able to find the median in O of 1 time without needing to sort the array. In that case, what is, you know, like your worst case, best case, average case time complexity? And in that case, because um, our cost of finding the median is now so low that we can effectively find the median every time, we would be able to guarantee that we always end up with the ideal pivot choice, meaning we always end up with O of n log n complexity rather than O of n squared. So our worst case behavior would get better. Does that make sense? Okay, cool. Awesome. So then in summary, um, we've basically got this nice little table. I would recommend, even though you don't have to make a cheat sheet for this exam, I found that it's typically helpful for me when I'm studying to go through all of my notes and condense it down onto another sheet of paper just so that I know that I've seen all of the information again and I have a chance to basically pick out the important parts of each lesson and kind of highlight those. Um, so I would actually still recommend making a cheat sheet. You know, you don't have to limit yourself to only having one anymore, but definitely going through all of your notes and condensing the information in a way that is easier to look through during the exam and is more helpful. And also you'll probably remember more of it during the exam, so you won't have to look at your notes as much, is super helpful. And this is one of those charts that I would recommend putting on that cheat sheet, just because it has a lot of really helpful stuff. Oh, I guess we didn't really talk about heap sort. Um, for heap sort, you're basically just going to make a heap, and then you're going to sort it. No, for heap sort, it's a little bit easier. I think we took out the slides on that just because it's not as big of a focus for now, so wouldn't worry about it too much. Okay, any other questions on sorts? Okay, sounds good. Then in that case, let's move on to actually real quick. Show of hands in the chat. Does anyone want like a 2-minute really quick break? Get some water, stretch. Okay, awesome. Let's do a quick break and let's be back at, let's say 4:17 or so. And then we'll be back and refreshed and ready to do binary search. Okay, awesome. Oh, this is super cool, Kevin. I actually had not seen this this exact gallery. I did recently see Also on Imager, I saw a gallery of sorts that did, they sorted like color pixels in an oval. So they like went around. Let me see if I can find that. Search sorting. I found this one, which covers a lot of sorts that we don't necessarily sort or cover. So like we don't cover radix LSD sort or gravity sort. But I ran across this one and I thought it was cool. But this other one is also nice. I really like the visualizations of sorts because I feel like if you run them all at the same time and the same speed, you can typically kind of see which one moves the fastest, and it can kind of give you some intuition as to like, oh, this one does fewer swaps than the other one, and so that's why we typically use it, even though they have the same average case time complexity. This one just in practice works faster. But this is super cool. Nice. Also, visualizations are just so pretty. Oh, yes. So the question was, for heap sort on the previous slide, what does it mean by distinct keys for the best case? So in the worst case of heap sort, all of your keys are the same. And then I believe your worst case becomes, or no, your best case becomes O of n, because you don't have to do any fix up or fix down. And so if you have distinct keys, like if you're using the heap for what it's really used for, and you're not just using all of the same element, then your best case is n log n, because you still need to pop off elements and sort it. But if you have a heap of, like, let's just say you have a ton of 5s, then no matter what you pop off, you're never going to have to call fix down. And so in this case, your pop function will only be O of 1 rather than O of log n. And so when you pop n elements, so you can create your heap in O of n, and you can pop off n elements in O of 1, giving you just O of n time. But if you use it for what it's actually meant for, right, if you're using distinct keys, then when you pop off an element, you'll still have to call fix down. And so you'll end up with n times O of log n over here, and so you end up with n log n overall. Yep. All right. Oh yeah, sorting algorithm visualizations are the bomb. Oh, also there's a group of traditional dancers um, who will do sorting algorithms by dancing them. So there's bubble sort. I'll post the link to this in the chat too. But you can watch people do bubble sort as a dance, which is also very, very fun to watch. Yeah, lots of good visualizations out there. All right, awesome. So welcome back from our little break, everyone. Yes, CS German double major. Best case use for that is just doing traditional German dances to sort, doing dancing visual sort algorithms. That's the way to do it. All right, so switching topics a little bit here, we're going to talk a bit about binary search. So binary search is a classic topic for interview problems. And so what we're going to work through here is basically, how do I take an initial problem and, looking at it, break it down into components that make me think, oh, maybe I can use binary search on this. So typically, if you're doing something like a coding interview, or even if you're just kind of standing in front of a coding problem, one of the things you're going to need to figure out is, which algorithm do I want to use? And so typically there are a couple of kind of like identifiers for specific algorithms that'll kind of point you towards them. And for binary search, we're going to go through a couple of different examples to try to figure out what those might look like. So to start off, real quick, let's think about binary search in general. So the way that I like to think about binary search is, you're basically going to have 3 parts. You're basically want to be able to check if something is equal. Otherwise, if something is greater, and if something is less. If something is equal, you know, okay, I found the thing I'm looking for. Otherwise, if I know comparing various or comparing something about the information I'm given that I am like greater than my current location, then I can move to the right. Or if I'm less than my current location, I can move to the left. Then I can basically take a large problem and break it down into something that can be modeled by a binary search, right? So in the typical case of, let's just say that we have a sorted array, and I'm basically just looking for a specific element, right? I can, let's say that I'm looking for, I guess let's look for like 4.5 or something like that, right? I can start at the middle. I can compare these two. I have information about these two that I can compare that tells me if I'm equal. Otherwise, I have information that I can compare just looking at these two elements, right? The thing I'm looking for and the thing that is there, right? I'm looking at this and I'm trying to figure out, okay, do I move to the right or to the left? Just looking at these two elements, it tells me which direction to move, right? Because 4.5 is greater than 3, I can move to the right. If I were looking for 1.5, 1.5 would be less than 3, so I'd know I need to look to the left, and then I can keep going from there. So if we can identify this type of behavior, right, looking at a specific number of elements, determining where I need to be, if I need to go to the right or go to the left, then I can basically set up a problem with binary search. So let's say that we're given this specific question. You're given an array that is first increasing and then decreasing. We want to find the maximum value of this array. So to start off, without even thinking about binary search, what are some approaches that we could take to solve this problem? We could figure out where it switches from increasing to decreasing, right? That's even a step ahead. We could do an O of n linear search, right? Awesome. We could just loop through all of the elements. Or we could even, sort it and then look at the end element. Exactly. Like Eugene said, we could sort and then look at the last element. So essentially, or sometimes how it goes in these interviews is you'll start off with one idea, and then as you work through the problem, you'll realize that there's an even faster approach to it. Or, it might not work in a specific scenario. So let's say that we start off with the idea, okay, let's sort it and then look at the last element. And then maybe your interviewer or maybe something in the problem will say, oh, well, actually, you can't change the ordering of any of the elements, and we don't want you to use extra memory. Then in that case, okay, I need to do it in place, so I can't copy any elements, nothing like that. Okay, I can't just sort it and look at the last element. I'm going to need to look at something else. Then you might think, okay, then I could do an O of n linear search, or maybe something in the problem statement. This is actually what's really nice about 281 exams. For the handwritten problems, we tell you the time and space complexity, and those are typically a pretty big hint as to what algorithm you want to use. So let's say that for this type of a question, we gave you time complexity O of log n. Then we know that we would want to use binary search. And so let's go ahead and, based on what Kevin said, right, figuring out where it switches from increasing to decreasing, let's try to basically go ahead and visualize that. So I like to visualize this by, let's imagine that we have our array, and let's say that this is our index, I, oops. And then let's say that over here we have our array at I. So if we imagine our values, we're going to first increase and then decrease. So maybe I will end up with, something like this. But I might also end up with something that looks a little bit more like that, right? Or I might end up with something that is increasing and then decreasing, something like that. And so basically, once I know that I have a binary search problem, what I try to do is I personally try to draw out a couple of different scenarios that I can think of. So I basically want to come up with some edge cases. So this, for example, is a really good example of an edge case. Basically, it's saying that it's first increasing and then decreasing. In this case, the entire array is first increasing. There's no decrease. So I need to be careful on this one. I need to know that I need to grab the last element here. Okay, so I'll keep that in mind as I'm writing my algorithm. Same thing with this one, right? The opposite edge case. I start, there's no increase and then all decreasing. So I know that I'll need to grab the last element. and then a couple that kind of generally represent other scenarios, right? So in this case, I might have something that is, exactly peaked, or I might have something that's slightly skewed to one side or the other. Once I'm able to visualize this problem and all of the different types of inputs that it might give me, then I start to think about those three components of my binary search. So thinking of this together, exactly, this would be like regular binary search, except instead of comparing the current value against the values you're trying to find, we're checking if the value to the left or the right is increasing or decreasing, or we don't know what part of the array to continue searching in. Exactly. Or not to know which part of the array to continue searching in. Right, exactly. So let's go ahead and break it down into those three exact components. So how do I know if I've found the maximum value? What elements can I look at a specific location in the array to know that that is the max? The value to the right will be less than it. Exactly, right? Because we always increase and then we decrease. So that means that array at I plus 1 is less than array at I. That's going to be how we check if it's equal or if we're on an edge. Exactly. So if we're on an edge, then we might have to add another little check to make sure that we don't go out of bounds for the array. Awesome. How do we know? Now let's say, is everyone okay if I clear this real quick? The drawing? Okay, I'm going to go ahead and clear this. Now let's say that we have something like this, and I'm located right here. How do I know whether I need to do... So in this case, we're only ever first increasing and then decreasing. So we don't have two peaks that we need to worry about. We only need to worry about one peak. If this weren't a case, then we would have to be careful and we might not be able to apply binary search anymore. Exactly. So let's say that we're at this location. How do I know whether I need to move to the left or to the right of where I'm located? Greater than the one before. Exactly. So we're basically trying to figure out, am I on the upslope or am I on the downslope? And I'm on the upslope if I can basically check the element right before me and the element right after me, and I see an increasing trend. So if a of I minus 1 is less than a at I, and a at I is less than a at I plus 1, oops, a at I plus 1, then I know that I'm on the upward slope. That means I need to keep following that slope upwards. I need to go to the right-hand side in order to look for the maximum value. And then for, if we're on a decrease, if we're located right here and we need to move up here to this top, then we'll basically have the inverse relationship, right? We'll end up with a of I minus 1 is greater than a of I, and a of I plus 1 is less than a of I. So we need to move to the left. Awesome. And now that we have these three components, we can basically go ahead and write our binary search. Right? So we basically end up with our three cases here. If the middle element is greater than both of its adjacent elements, it's the max. If the middle element is greater than the element to its right and smaller than the element to its left, then the max element lies to the left of the mid. So we're on the decreasing side of the array. And if the middle element is smaller than the element to its right and greater than the element to its left, then the max element lies to the right of the mid. We're on the increasing side. Okay. Any questions on this first example? Is it guaranteed that there are an odd number of values in the array? How would we choose the middle if there were an even number, or would it not matter? Great, so that's a great question. If there were an even number of elements, we would basically just go ahead and do integer division. So let's say that we had 8 elements. To find the midpoint, we just do 8 divided by 2 gives us 4, and we just start at that index. So our sides might be slightly larger or slightly smaller, but that's totally fine. Yep. And then the question is, does I always start at 0? Um, yes, so we would start at mid. So we'd follow the same behavior as a typical binary search. So we would start at the midpoint, look here, and then we would basically decide, okay, do I just consider the left-hand side of the array or just the right-hand side of the array? So if I end up deciding that I just want to use the left-hand side of the array, then I would again go to the midpoint there, basically ignore all of this, and then take a look there. And so basically, the nice part about binary search is that essentially we're always, they call it like cutting down your search space, right? So if we think about something like merge sort, right, when we split our two parts in half, we still have to do work on one side and then the other, and then combine the two together. With binary search, what we're doing is we're actually just always making our search space smaller. We're never returning back to anything. We're never considering the other side too. We're only ever like decreasing the amount of space that we're looking in and then continuing to look there. And then checking, can we, make this search space even smaller? What about the edges? The edges we could basically consider the edges in this case if we end up like if we let's say that we have our max element over here, what would end up happening is we would basically always choose to go to the left until we ended up with n equal to 1. And then at that point, we know that our maximum element is located at index 0. So our edges are kind of handled in this top case here. We could explicitly also write those in there. So in our checks where we're doing I minus 1 and I plus 1, we would first want to make sure that we're not going out of bounds of the array there. And other than that, everything else could be handled here. Because our trajectory would take us all the way to that edge if the item is located at the edge. Any other questions on this first question? Okay, awesome. So then let's go ahead and the edges of the array are going to become important in this next problem. So for this next one, let's say that you're given a sorted array that is rotated at a certain position, and we want to return the minimum element. So for this case, I'm going to go ahead and why don't you take 7 minutes or so until 4:40 and just try to go through some of these examples and figure out what we need for our equivalent comparison, what elements we need to look at or what we need to compare for our greater than, meaning we move right, what we need for our less than so that we move left. So go ahead, take some time to do that, and we'll check back in at, let's say, 4:40. Actually, real quick, let's go through a visualization of this first, and then I'll turn you loose. So let's say that we start off with a pre-rotated array. And note that this is a sorted array. So that means that all of our elements are increasing. If we rotate it, it's basically going to end up looking something like this. So let's see. That's kind of like the height that that starts at, and then we'll end up with taller elements here, like that. That didn't really get lined up nicely, but that's essentially the kind of motion of it. Okay, now you can get back to it. All right. So let's go ahead and think through these three specific scenarios. So in the chat, why don't we share some ideas for what we could potentially use to determine whether we found the minimum element? So if the element on either side is greater than the current element, then we know that we found the minimum. Could we do that in even fewer comparisons? All good, no worries. What other check could we use for if we're at the minimum element that we don't even need to check both? We could compare the midpoint to the rightmost element. So in this case, oh, for the greater than and less than cases. Yes, that'll be helpful. For the equal check, we could even also just compare to the element immediately to our left, right? So our minimum element is going to be the only element whose element before it is greater than it. So we could check if I minus 1 is greater than a of I, then we're at our minimum element. Awesome. Now, as Evan and Eleanor have talked about here, when we're doing our check for our greater than or less than operators, we're basically checking, in either case, if I'm located over here or I'm located over here, I'm always going to be kind of on this increasing trajectory, right? So I can't just look at the trajectory itself. Instead, what we want to check is basically like looking at this element and comparing it to our last element, we can figure out whether we're on the increasing portion that is before the rotation or the increasing portion that is after the rotation, right? So I'm going to go ahead and clear this drawing. And let's imagine that we have something like, so let's imagine that this is kind of our cutoff, and let's say that we rotate like this. So this is kind of what our sorted array looks like. If we are located over, oh, I guess I should have drawn this a little bit less centered. I'm going to go ahead and clear this again. And then just so that we can kind of have a couple of different examples, let's try this one. There we go. And let's say that we start at our midpoint here. So if we want to determine whether we are on kind of like the increasing portion or if we're on the increasing portion that contains the minimum at the left, or if we're on the increasing portion that just goes up to the maximum element, we basically want to check also our kind of last element here, right? So if my current element is greater than my last element, then I know that I'm currently located in the portion of the array, or that everything to the left of me is going to be just increasing, and everything to the right of me eventually will have that breakpoint in it, right? Because otherwise, there's no way for me to get this distance between me, if I'm on the left, let's compare these 2 points, right? If this point A is greater than point B, and point A is to the left of point B, then at some point, there must have been a jump in there. Does that make sense? Could you compare instead to array 0? We could also compare to array 0, I believe. Array 0, I think, would be a little bit less helpful because it's sorted greater than. So as Eleanor says, it will usually be less than. So let's imagine, for example, a scenario like this. If it's all increasing, if we didn't have a rotation, then if we're located here to find our minimum element, looking at our array point of 0 isn't really going to give us more information. Yeah, so we're always going to look at, so we basically look at the end to figure out, okay, does the break, so that rotation break, does that happen to the right of me? And if it doesn't happen to the right of me, then I'll move to the left. So basically it looks a little bit like this. So we check the middle element. If the element to the left is greater than it, mid is the min. So that's going to be our equal comparison. If the element to the left is less than or equal, it's not the minimum, which means the minimum has to lie either in the left or the right half. If the middle element is smaller than the last element, then we had that rotation break is in the right. Rotation break in right, so we want to move right. Otherwise, that means that it's still going to be in the left-hand side, so we're going to go ahead and move to the left. Yeah, I think we have this flipped a little bit, but it's the same logic. And then when you've narrowed the minimum down to 2 elements, you can compare their values to find the min. So in certain cases, you'll end up also needing to check the edges, I believe. But for the sake of time, we'll move on. Any other questions for this one? On the midterm, okay, so one question. On the midterm, would we be given questions like this and be expected to explain all conditions? So this is the type of question that you would actually see for more of a handwritten problem. So for example, this might come up with, we say you're given a sorted array that is rotated a certain position, return the minimum element, you have O of log n time complexity and O of 1 additional space. And so those two, so for time and space, those two complexities will kind of point you towards binary search. And then we would expect you to actually write out the binary search, kind of writing those three specific checks in there, and making sure that you handle all edge cases and stuff like that. So what we're practicing right now is also kind of taking that idea of like, okay, I have these time and space complexities, so it's probably something like binary search. I'm going to go ahead and see if I can figure something out in order to answer this with a binary search algorithm, and taking kind of like those specific steps to break it down into some pseudocode, and then you would take that pseudocode and actually go ahead and write it out as C++. Okay, awesome. So then let's take a look at question number 3. So this is our last binary search example. So this time we're given a sorted array. And notice that all of these have sorted arrays somewhere, because sorted arrays allow us to get that additional information, right? If it were just a random array, we wouldn't really be able to figure out like whether we're increasing or decreasing or anything. We wouldn't be able to figure out anything about the rest of the array from our, one specific current location. And so because it's sorted, we can derive more information from our current location because we know what the rest of the array kind of looks like, or the general trend that it has. So based on our location, we can figure out where other information might be located. And so in this one, again, we have a sorted array. So we've got the sorted array. Every number occurs twice, except for one number. Find this number that only appears once. And so in the chat, we've got the half of the array with the lone number in it will have an odd number of elements. Right, so this entire array will always have an odd number of elements. And if we think about our indices, we'll be able to think of how those relate. So let's go ahead and place our indices below these numbers. Oh no, this is about to get really ugly. Okay, that kind of worked. 4, 5, 6. And so again, let's go ahead and let's just do like 3 minutes. So we'll reconvene at 4:52. Go ahead and see if you can again figure out what checks you need to do for equals, greater than, and less than. All right, so what do we have as the order of pairs don't necessarily have to be in order, right? So it could be 661199. That's true. We could, this problem would also work if we only had the stipulation that if two numbers appear, they appear together. Or sorry, if the same number appears twice, they appear together. So it could also, the same algorithm that we'll use to solve this for the sorted arrays could also be true if the pairs themselves can be in any ordered. So what ideas do you all have for, first off, let's start off, how do we know if we found the number that only appears once? If adjacent numbers are not the same, exactly. So if a plus, oh man, if a of I minus 1 does not equal a of I, and a of I plus 1 does not equal a of I. Awesome. So how about figuring out whether to move to the left or to the right? First off, we know that we need to move in one of those directions if one of these adjacent numbers is the same as your current number, right? So if I'm located here at index 10, then I know that I need to move either to the left or to the right because index 9 is the same value. So what other information can we use to determine whether we move to the left or to the right? So if the higher number is the same and an even index, or the lower number is the same and an odd index, then we want to move to the right. So if our higher number is the same and an even index, oh yes, and I is at an even index, right. So as Eleanor's identified, if we take a look at these pairs, so let's take a look just at this first example, and let's look at how the pairs are ordered before the individual number and after the individual number. So before the individual number, we see that pairs always start on an even integer, right? We have 0, 2, 4, 6. Afterwards, the pairs start on an odd integer, 9 and 11. And so to determine whether we're before that first individual number, or sorry, if we're before the individual number or we're after, we can basically look at this pair, identify, okay, you know, like depending on if I'm located at index 4 or index 5, I need to figure out if I'm the second of the pair or the first of the pair, and then I can look at the index of the first of the pair, and if it's even, I know that I'm to the left of the individual number, so I need to move to the right, and if it's odd, then I know that I'm to the right of the number and I need to move to the left. Awesome. And so we have that summarized right here. So basically, if there were no odd element out, the first occurrence of each number would be found in an even index, and the second occurrence would always be found in an odd index. That's true until we reach the odd one out. Once we reach that point, the opposite is true. So we're basically always going to go ahead and check whether we're the first or the second of that pair, and then which index the first of that pair occurs on. And so based on that, we'll move either to the right or to the left. Any questions on this third binary search question? Okay, looks like there aren't any questions. If you're typing a question, keep typing it and I'll get to it. But otherwise, I'm going to go ahead and introduce the handwritten problem. And then that'll be it. So your handwritten problem for this week is, or for this lab, 2 labs a week in the summer because it's fun. Given a vector with n elements with values of either 0, 1, or 2, you want to devise an O of n algorithm to sort this vector. You must do this in a single pass of the vector. You may not copy items, create arrays or strings, or do any other memory allocation. And you want to make sure that your algorithm works for all cases. So you can use standard swap to swap two items in the vector. And so here is your function declaration. I'm going to go ahead and give you a couple of pointers. My one pointer is that you should use pointers or indices or something, but essentially keep track of those. And then the other hint that I have for you, so I guess if you don't want this hint, feel free to like take off your headphones or mute me or something for a second. But the other hint that I have is that you remember how in the sorted, when we were talking about sorting algorithms, we talked about keeping a sorted portion of the array? That's basically what you also want to think of here. So how can we think of keeping portions that are entirely sorted in their own, or considering a certain portion of the array or the vector to be sorted? So we had one question, O of one memory. Oh, yes, so O of one additional memory. So we have, you may not copy items, create arrays or strings, or do any other memory allocation. I think you can do, I don't like what it says with any other memory allocation. You can still create like a constant number of atomic elements. You just shouldn't allocate like an entirely new vector. Yeah. Because otherwise it doesn't work. Okay. Any other questions on this handwritten problem or anything else that we covered in lab? What's the exam format like? Okay, great question. So the exam is going to have two components. It'll have the multiple choice section will be a Canvas quiz similar to the lab quizzes. And then you'll have unlimited submits, I believe. Basically, you can still change your answers. Or no. You submit it once and you're done, I think. Yeah. You'll have 2 hours to complete. So you'll have that component, and then you'll also have the handwritten questions. The handwritten questions will be at the bottom of the Canvas quiz. You'll submit your solutions to those to Gradescope to the exam question on there, and then we'll grade them from there. And I believe the professor should also give some more. That is a good question. Will handwritten be on paper? I'm gonna double check real quick. I don't know. Let me ask. On the exam. Okay, I don't know if someone will get back to me in time, but the professor should also be clarifying that in lecture soon. Right. So it will be. Oh, so the exam itself, the handwritten questions will be given to you via the Canvas quiz. I don't know if it'll be a PDF or some kind of editable document, or if you just write your own and submit it. You'll have 2 hours for both the multiple choice and free response together. And if you have extra SSD accommodations, you'll have extended time. So you'll allocate your 2 hours to complete both the multiple choice portion and the free response. So what I actually typically recommend is I recommend students go, when they first get the exam, when they open up that Canvas quiz, scroll all the way to the end, take a look at those free response questions and just start mulling them over in the back of your mind. Go through and complete the multiple choice section, skipping questions that you'll come back to and stuff like that, and then make sure that you have enough time at the end to actually go ahead and write your free response answers. So I typically try to take at least an hour for the free response questions. So you'll allocate your time individually. Yeah. Awesome. Any other questions? Okay. Then in that case, thanks for participating so much, y'all. It made it almost feel like it was an in-person lab. When is this due? Oh, the question for the CPP file for the handwritten problem. Oh, I did not upload that yet. I will make sure to write one and upload it for you both, or for you all. And then this specific lab, so lab 5 and lab 4, the quiz components are due at 6 p.m. Oh, great. 6 p.m. on Wednesday. That's so that we can release the answers to you so you can use those to study for the exam on Thursday. And then the lab 4 autograder component is still due on next week, Friday at 11:59 p.m. So only the 2 quiz components are due 6 p.m. on Wednesday. Okay, awesome. Like I said, thanks for being so active in the chat and for working through these practice problems. Hopefully this was helpful. If you have any more questions, feel free to post on Piazza or to come to my office hours and I'll try my best to help. But other than that, I'm going to go ahead and sign off. And I hope you all have a great rest of your week and weekend. Bye, y'all.